All right, welcome back. Let's do linear congruence. So we're going to tie this together. We're now going to use this to actually solve some problems. So going back to Diophantine equations, specifically, we now want to consider the equation. I'm using that term a little loosely because it's a congruent. AX is congruent to C mod N, but I don't know what X is. I want to solve for X. This actually ties into Diophantine equations because what we can literally say that this is the same thing from our last discussion, that this is AX minus C equals N to some times some power. Or in other words, that means the Diophantine equation AX minus NY is equal to C. So notice we have a Diophantine equation that we are trying to solve. Now notice, by the way, the roles have changed. Instead of A and B, I have A and negative N. It's a little bit different, and that will be important. All right. Hence, the solution exists if D is the greatest common divisor of A and N, then it must be the case that D divides C. So if there is a solution, then D must divide C. Now, if the greatest common divisor of A and N is 1, then obviously there is a solution. This D is going to be important. And further, our solution is AX0, Y0, so we know AX0 plus N over DT, Y equals Y0 plus A over T. So how do we find this? How do we find these values? Well, as a quick reminder, back when we did this, we can solve this using the Euclid's extended algorithm. If I noticed on the last homework that many of you were just simply apparently guessing checking. There's no work support. You just magically came up with the numbers. Again, we don't just magically come with numbers. There's actually processes that we can do these things, and we don't want to brute force just I found it. That is not efficient. So to solve this, we are really solving the equivalent, the congruence then. We're talking congruence is how many incongruent solutions are there? So in other words, are there incongruent solutions are there to the equation mod N? So it's, for instance, so I'm talking mod 5, 1 and 6 might be both solutions, but I don't care. I would just take 1. However, 1 and 2, if they were both solutions, that would be a different matter. And we actually have a really cool theorem dealing again with the greatest common divisor of A and N. If D is the greatest common divisor of A and N, and if it divides C, then the congruence has a solution. Not only does it have a solution, it has exactly D incongruent solutions. Oh, so that means if I do this, it will have, by figuring out that greatest common divisor, I can actually figure out how many incongruent solutions we have. So the proof of this is very simple. Let's let, well, I don't know if simple is the right term, but the proof is, I think, straightforward. It builds on everything we've done so far on extended Euclid algorithm. So let's let X0 be a solution. So we're going to start with a solution. Because we already know that all solutions are then of X0 plus N over dt, where T is any integer. So now we want to find out which of these are not congruent mod N. Well, since I have X1 and X2, notice I have two different T values, T1 and T2. Well, they both have an X0 and so forth. So X1 minus X2, the X0s will cancel out. I can factor out the N over D. And if X1 and X2 are congruent mod N, so if we're actually going to consider the situation where these are both congruent to each other, because if they're not congruent, then we just do the opposite. So they're congruent exactly if N over D is a multiple of N, meaning that N over D times T1 minus T2 is equal to K times N for some K. But if I go ahead and cancel out the ends and multiply the d to the other side, we get T1 minus T2 is equal to KD, or in other words, T1 is congruent to T2 mod D. Here's a different way to think about it. So I'm going to write this down and write a note right below here, and then I'm going to continue on. So if I have, for instance, 2 is congruent to what? Mod 5. Well, it's congruent to 7. Also, so if my D is 5, then all I would do is take 2 and I would add 5, and then I would add 5 more and I get 12, and I add 5 more and I get, you all get the idea here. So continue on summing up, the solutions then are inequivalent, are exactly the ones that are corresponding to D that are inequivalent mod D. So as long as they are inequivalent mod D, then they're inequivalent mod N. And there are D such classes because we can do every value from in mod D, there's D of them for T. And this proves our theorem. So again, I'm going to go back to the theorem because I want to emphasize this. If D is a greatest common divisor, then there are exactly D incongruent solutions. We have D solutions to find. So we need to find greatest common divisors. We need to solve extended Euclidean algorithms, etc. So let me do an example to wrap this up. We want to find all the solutions to nx is congruent to 12 mod 15. What we do here is first and foremost, we say, what's the greatest common divisor of 9 and 15? Well, it's 3, and that divides 12, so we have a solution. So this tells us we even have a solution. If we didn't have a solution, then that would be a problem. By our previous theorem, we have 3 solutions that we have to find. And this is the key thing. So I know I'm not done until I have 3 different solutions, mod 15. To find these, we can utilize Euclid's extended algorithm. So we start here and we go through the process until we find 9x. We find the x and we find the y. Remember, that's a whole thing where you start off and you're like, okay, 15 is equal to 9 times 1 plus 6. And you keep going. And then we have, I'll go ahead and do the next one. And then 9 equals 6 times 1 plus 3. 6 equals 3 times 2. Then working backwards, we get, well, this one right here is actually good enough. Working backwards, we get 3 equals 9 minus 6 times 1. And this one is 15 minus 9 times 1 is equal to 6. So I can do 9 minus 15 minus 9 times 1 is equal to 3. So it's 9 plus 9 times 1 minus 15 equals 3. So 2 times 9 minus 15 equals 3. What that means is then y is -1 and x is 2. Erasing this so I can actually pull up my next notes. I actually, if we solve this, again, I'm just doing that extended algorithm, this is what we did before, then we actually know that x is 2 and this is a solution. But however, notice this was to get us to have x equals 3. We want it to be 12. So just like we did before, we take our solution here and we multiply it by 2. Since 9 times 2 is congruent to 3, then 9 times 8 would be equal to 12. Because if I just multiply both sides by 4, which tells us that 8 is a solution. But since 8 is a solution, what we can actually do now is everything's of the form 8 plus 15 divided by 3. So I take my mod and I divide it by my greatest common divisor, which is 3. So this is 8 plus 15 divided by 3. Well, the only options, and there'll be 3 values, 0, 1, and 2. You don't need more than that. And you get from that, your numbers are 3, 8, and 13. If you plug in the 2, by the way, that's where you end up with the 3 situation. So these are our solutions. 3, 8, and 13 are our 3 different solutions to this particular equation. Now, again, notice we are leveraging our Euclid's extended algorithm. We're using greatest common divisors. We are leveraging modular arithmetic. So all of this is coming together to solve these particular problems. I hope that helps. Please let me know what questions you have. Don't forget to jump on the discussion board, and good luck.